want to find a zigzag phase near the ferromagnetic cadet limit by looking at the simplest consistent model, and all I found were incommensurate spirals. So let's go to the next simplest model. So one could, in principle, add monoclinic distortion, trigonal distortion, further neighbor couplings on that trigonal distortion. So in the crystal structure, the sodium has a trigonal compression out of the plane. If you sort of go through this, you can find that it introduces a single nearest neighbor coupling in addition to the three you already had. So it's sort of a cousin of this symmetric off-diagonal exchange. Instead of for example, on the Z bond, instead of X and Y coupling, you have X and Z coupling and Y and Z coupling. And if you do sort of a rough microscopic calculation of this, for trigonal compression, you might expect it to come out negative. So I'm just sort of going to focus on adding a negative gamma prime when thinking about this sodium iridate. Okay, so what does that do? So classically, as I told you before, the zigzag phase in this one spiral phase were actually quite close in energy, and it turns out adding this negative gamma prime actually tips the balance towards the zigzag phase. So this one phase that occurred here is almost completely overtaken by a zigzag phase. So this is actually quite a small gamma prime. It's maybe a 20th of K, and it completely enlarges this phase and brings it down almost to this ferromagnetic cadet limit. Again, you might ask, how does this hold up away from the classical limit? I've sort of changed the phase diagram, but here, in the middle of these plots is the cadet limit here. Gamma goes up, and then J is running along the x-axis, and then each slice is a different value of gamma prime. So here you see this mess that we saw in the exact diagonalization that I associated with maybe the stripy phase classically. And then as I turn on a negative gamma prime, you see these zigzag correlations start to develop. So this is consistent with the expectations from the classical calculation. Okay, so we've sort of partially answered one of the questions. Can we find a zigzag phase within this simple model, or second simplest model, close to the ferromagnetic cadet limit? So it seems like we can. Can we explain why this energy scale and the spin excitations is so small? So in these highly anisotropic models, you don't really expect to find things like Goldstone modes, right? Unless you have a classical degeneracy like in this HK model. So generically, you would expect this, as soon as you include this gamma or this gamma prime, you would start opening up gaps in the spin waves, and if you made them significant, greater than 1 or 2 MeV, you wouldn't have these low energy excitations anymore. And microscopically, it's not clear that gamma should be small. There are some calculations, depending on how you go, there's disagreement on how large it is, but generically, it doesn't have to be small. So generically, you wouldn't expect these low energy excitations. So how do we put these things together? So we just sort of ignored this, and we went and tried to compute how big it was, ignoring this argument. Asked the question, how big is the gap if you include this gamma? So we just fixed the calculation into the zigzag phase, did a 1 over S, looked at the gap. And so what you find is that in this Heisenberg cadet limit for the zigzag phase, it's gapless, as you can find. And then basically everywhere else, it's gapped, except for this line here at large gamma. This was sort of unexpected when we saw it, which is if you increase gamma here, you open up a gap, but then for a significant gamma, somewhat comparable to the cadet exchange, the gap actually closes again. And beyond this, it's not a point, it's actually a line in parameter space. And if you include gamma prime, it actually becomes a surface. So there's something going on here. This second gapless regime for large gamma is surprising. So after we found this, there was this nice paper by Cherupka et al. Where they actually found a decent explanation for this, which is there's a duality in this model, essentially. So this JK gamma prime model is actually sort of self-dual under this transformation. So it kind of looks like a mess. But if you plug in that point or that line that I showed you, this large gamma line actually maps back to the Heisenberg-Kadeb model. And you have the accidental degeneracy again, and you expect gapless spin waves. And beyond this, there's this four sublattice duality in the original HK model that can map a point in the zigzag phase back to the Néel antiferromagnet. So if you trace this through, you can start with very large gamma, some gamma prime, a very large K. Then through the duality, you can map that to the HK model in the zigzag phase. And then from that point, you can map that back to the Néel phase, which is essentially not solvable in the exact sense, but theoretically tractable, right? Or you'd expect to find gapless excitations. Okay, so that's kind of the story for the sodium. Can we say anything about the lithium? So there are hints of ink-measured order, and this problem of finding the ink-measured order without gamma prime is actually essentially a blessing when we're talking about lithium. And it turns out if you go the other way with gamma prime, you make it positive, you actually enlarge these ink-measured phases. So as you see here, this phase that when I turned on a small negative gamma prime was all zigzag is now back to being this spiral. And this is sort of consistent with expectations from at least tentative crystal structures for this, where they look slightly less distorted. That's just kind of up in the air, but it's not inconsistent with the structure, the known structures of the lithium iridate. So what do these phases look like? So I just sort of picked a point in the middle of that phase. The wave vector, again, changes continuously, so it depends on exactly what parameters you pick. But there's a fairly sort of large plateau where the wave vector is near this 2m/3 point. So this is the Bruin zone here. This m is the wave vector of the zigzag phase. And there's a fairly large plateau where this q is actually quite close to that. So in the classical calculation, you can sort of just pin it to this 2m/3 wave vector, which is can measure it and sort of try to look at that as an approximation to your state. And what you find is a state that looks like this. It's slightly ferromagnetic. There's a threefold order to it. Not single Q, so there is a small ferromagnetic component, and the relationship between these two Bragg peaks is not exactly what you'd expect from a single Q state. But one interesting bit about this state is that the wave vector, if you put it in sort of physical units, is about 0.4, which is approximately numbers that have been reported, hinted at in the lithium iridate. So let me just summarize this. What we show here is that in this generic model, if we add a small amount of trigonal compression, we can stabilize the zigzag phase near the ferromagnetic Kadeb limit in a completely nearest neighbor model. Beyond this, looking at around small gamma prime, there's both this zigzag phase competing with this incommensurate spiral phase, which might have some relevance towards the lithium iridate. And further, this parameter regime, you can still have this large anisotropy, even these gamma terms, and still have a small excitation gap. And if you want details, there's two papers. Read it. Thank you.
I have a question about zigzag phase. When you talk about zigzag phase, are you talking about the continuous phase, or you're talking about the phase in which zigzag might be different? Because it's really my confusion. What the government